Welcome to the Picture Language Seminar. After our talk today, we'll take a break until January 25th, when Guoliang Yu, Director of the Center for Quantum Information in Shenzhen, will open our series next term. It's a great pleasure to welcome Guoliang Yu, a mathematical descendant of Ron Douglas. Guoliang made important contributions to the theory of invariants. He is internationally known as an expert in non-commutative geometry, index theory, and K-theory. Guoliang taught at the University of Colorado Boulder and Vanderbilt, and also has been active in the Mathematics Institute of Fudan University. Today, he is Distinguished Professor at Texas A&M and College Station. He will tell us about his work on higher invariants of Dirac operators and positive scalar curvature.
Well, thank you very much, Asa. So I will start to share my screen. Okay, it works. Well, thank you very much, Asa, for the invitation. And it's my great pleasure to speak here. I have to first acknowledge I'm not an expert in differential geometry. So if I say anything wrong, please let me know. I'm in the process of learning. And so because this, I understand that this seminar's audience is like very broad and very diverse. So I would like to make my talk as accessible as possible. So if you have any question, just like stop me. Okay, so I will talk about the connection of the subject of scalar curvature with Dirac operator. And so let me just first recall what scalar curvature is. I mean, scalar curvature actually can be defined in a very elementary way. Like, so let's say we have like an n-dimensional manifold with a Riemannian metric. Let's try to measure the ball with radius r, then compare the ball of the same dimension in Euclidean space, also with the same radius. Look at their ratio. And asymptotically, we have this formula. And when I is very small, and there is this constant, and this is what scalar curvature is. So what it means is that if scalar curvature is positive, then microscopically, volume is smaller than the volume of the same radius in Euclidean space. And if it's negative, it's bigger. Okay, so it's very intuitive. So of course, it's also very elementary, but with such a actually intuitive elementary definition, it's actually very hard to do anything with that. And because most of the interesting results are like a global, and it's very hard to use this definition to prove anything interesting. Let's, it's, although it's a very elementary concept, but it has many very deep results. And so I'm going to next to just mention a couple. These are just sample examples, and they're by some representative examples. They're by no means like the most general or the best result. I just want to show you like a couple of results which are quite deep. Well, the first one is about existence of such a like matrix with positive scalar curvature. And so here it's a general result, when you have a variety like this, when you have a homogeneous polynomial with degree at the most n, then it defines like a hypersurface in the complex n-dimensional complex projective space. And this actually has has a metric with positive scalar curvature. But the solution is to prove this, you need something very deep, like your solution of Calabi-Yau conjecture. So I'm not aware of any like elementary direct construction. Okay, so this is about existence. Now, what about non-existence? And so you see, for degree, like the first example here is very much along the same direction in the previous page. And so here we have a polynomial, homogeneous polynomial whose degree is now greater than the dimension, I mean, the complex dimension of the complex projective space. But for this, very nice looking, it's called one of the coma surface. And already it has, you can prove it has no positive scalar curvature. But the proof, again, this is a concrete, surface, but there's no like purely differential geometric way of proving it. You need something from operator theory, that's the single index theory. Okay, so this is already, quite, it's a global, very striking result. Now, the next result I want to mention is the n-dimensional torus. Well, actually, there was, for more than 20 years, I think it was an open question whether the n-dimensional torus has positive scalar curvature. I mean, it sounds like such a concrete question, the torus. I mean, we should be able to do anything with the torus, but this is proved by Xiang and Yao using minimum surface method, Gromov-Rosen using index theory. And both proofs are very, very beautiful. And okay, so now this general phenomena, the torus, what about the torus which make it impossible to carry like a metric with positive scalar curvature? And so conjecturally, any aspherical manifold. So aspherical means that, in English, the name, the letter A means not. So it's not spherical. What it means is the universal cover is contractible. Like the torus. The torus, the universal cover of the torus is the Euclidean space, of course, is contractible. So conjecturally, any closed aspherical manifold does not carry a metric with positive scalar curvature. So this was proved for, I forgot to write the condition, and proved that when the fundamental group is hyperbolic in the sense of Gromov. Okay, so using completely different method, using method from non-commutative geometry and like cyclical homology, high index theory, stuff like that. So, and this is a completely new method. And okay, but so I think this was in the 90s. So this more recently, so in the last year, and there was some very striking result. So the conjecture was proved in dimension 4 and 5 by Chodosh-Lee and Gromov. I think first by Chodosh-Lee in 4 dimension, then independently in dimension 5, Chodosh-Lee and Gromov. Okay, they use minimum surface method. So we actually we have been attempting to understand it from like say non-commutative geometry or Dirac Operator kind of method. So far, we have not been successful. And for us, it's very striking because in dimension 4 and 5, the fundamental group can be anything. And so yet they like proved it unconditionally, okay? And their proof used like minimum surface, also some kind of quantitative, I would say quantitative topology. Actually, some of the second part of my talk will touch on that subject. So some like very fine structure instead of, like cost method. Okay, so this, I hope I have shown you like a few sample, but very deep results. And you can see, so the depth of the subject, it's connected to a lot of different mathematics. Okay, So I would like now to come back to the question, what is scalar curvature? And so this is the question actually Gromov has been like asking. So I mean, he actually asked this rhetoric question, scalar curvature, who are you? And he wrote like in the last couple of years, he wrote like hundreds of pages of like papers asking for various questions, but they are all related to this basic question, what is really scalar curvature? Okay, now just to give you an idea what people are looking for, and it's in very much in the spirit of Alexandrov geometry. So this way of doing geometry, like about curvature, and for to give you like an idea. So let's just recall how in Alexandria geometry, how you would like define curvature to be non-positive. Okay, so it's like really like almost like doing plane geometry. So what you do is like any metric space where it makes sense to talk about geodesic. So it's like a geodesic space. If you have like, if you have a geodesic triangle, okay? So this is a geodesic triangle. And so you compare it, so this is in any space, you compare it with a triangle and whose corresponding side have the same length. So this is just in R2, okay? So this is like any path metric space, X, say. And so now, let's see this point, let's call this point A, B, C, and then the corresponding point A prime, B prime, C prime. Okay, so you just take any point here, and if you measure the length, then there's a corresponding point here, P prime. And so the way like curvature is defined to be non-positive, and it means for any like geodesic triangle like this, the distance between A and P is less than like the distance of A prime, P prime. Okay, in any situation like this. So it's almost like playing with doing plane geometry. Now, what is good about this is no like derivative is taken, and everything is done just in just by measuring distance. So it's kind of C0. So this is like C0. Okay, so this is what we are looking for, like the spirit, like what is about scalar curvature. Okay, now let's look at like in dimension 2, like this. Actually, for scalar curvature, geodesic triangles are not good enough. So let's try to get some inspiration in dimension 2. Okay, so like if we have a Riemann surface. Okay, so I'm going to like also draw some kind of triangle. Okay, so it has 3 pieces, like 3 pieces, C1, C2, C3. Okay. So I have like 3 angles, theta 1, theta 2, and theta 3. So this, in general, we will call this the dihedral angle. Okay, all right. So now, of course, so we all know, the 2-dimensional Gauss-Bonnet theorem, and so we have. So let's write down the Gauss-Bonnet theorem, Ci, I from 1 to 3, and this is like the geodesic curvature, and then the curvature. So let's call this region the triangle, just triangle. and the curvature, then plus the sum of these angles. And well, if it's a triangle, so the number is 1, so we get 2 pi. Okay, all right. So okay, so now we want to do a comparison. So comparison with, say, Euclidean case. Okay, so we want to, like here, let me see, let's see, I have angles. I'm going to call theta's sigma 1, sigma 2 prime, and sigma so prime. Okay, so to do the comparison, let's assume that the geodesic curvature, so it's convex, is non-negative, and the curvature is also non-negative. Okay. And now, so if that's true, but let's assume that's sigma. Okay. Then from this from the Gauss bonnet, if those are positive, if this is true, then you can see that it implies the geodesic curvature has to be 0, the curvature has to be 0, and also all those angles has to be the same. Okay, so this is actually in this dimension 2. This is called Dihedral rigidity. Okay, so it's quite easy. So this is like suggesting how things should be in high dimension. And okay, so you see, it's very natural, like, because if you assume all the angles theta I is less than or equal to theta I prime, and from this identity, it forces, all the positivity forces this to be true, and it has to be like exactly equal. Okay, so this is, it's very much in the spirit of Alexandria of geometry. It's some kind of comparison theorem. Okay, so here it's what happens. So actually Gromov conjectured that this should be true in high dimension. So here is like the simplest version of the generalization. Okay, so and so if you have a convex polyhedron in Rn, and so if you have a Riemannian metric on that polyhedron, okay, and so now the geodesic curvature is replaced by mean curvature. Okay, so non-negative on each face. That's the codimension 1 face. Let me emphasize codimension 1. Okay, assume also the scalar curvature is non-negative, and so G0 is a Euclidean metric. So we are comparing the Riemannian metric on the convex polyhedron with just a Euclidean metric. Okay. All right. So we assume the dihedral angle. So dihedral angle are just the angle between two like codimension 1 faces. Okay. Is less than the dihedral angle of the Euclidean metric. Then the mean curvature has to be 0, scalar curvature has to be 0. Oops, I wrote something wrong, sorry. So this should be, that's a typo, ij G0. So the dihedral angle should be the same. Okay, so this is a natural generalization of what happened in dimension 2, you know, which was obtained using Gauss bonnet. Okay, any questions so far? So this is the simplest case of the so-called dihedral extremality or sometimes, well, dihedral rigidity, there's some stronger consequence, but I'm not going to get into those technicalities, okay?
Excuse me, is there, so what is actual this angle? Is it like an average angle?
No, this is pointwise. This inequality is pointwise. Okay, you can compare it. Yeah. So actually, I will state a much more general theorem where, you know, you don't have to be like convex polyhedron. You can any manifold with corners, any Riemannian manifold. So what I'm going to talk about is true in general. So, but I'm worried about, you know, because our audience has very diverse background. Let's focus on this case, just a convex polyhedron. But I will mention the most general result. It's about general manifolds with corners. So I actually, you know, the difficulty with proving something like this is, you know, so a polyhedron is a manifold with corner. It's the singularity coming from the corners. Okay, that's the difficulty. And okay, but before, you know, this sounds very elementary, but it has far-reaching consequences. Let me, but before I try to convince you this is something interesting, let me talk about something which is quite dear to my heart. Actually, is trying to like make sense of scalar curvature for singular space, or for manifold with non-smooth like Riemannian matrix. You know, the matrix is not differentiable. Okay, and the reason I'm very much interested in this is quite many years ago, I give like a counterexample of this so-called the geometric Novikov conjecture. I mean, that's a conjecture which is I worked on for many years. Using scalar curvature, you know, I logically it's a correct counterexample, but I feel like I never understood that example, because why do we need to use scalar curvature? So I feel like if we really understand scalar curvature for like more general spaces, you know, not necessarily smooth spaces, then one should be able to come up with a counterexample for the usual Novikov conjecture. So that's the reason, I mean, my own reason to be interested in this. Okay, so here is like, you know, a possible generalization of the concept of scalar curvature to singular spaces, you know, like inspired, if Gromov's conjecture is true. You know, at least it defines what non-positive scalar curvature is. And so you can say there exists no convex polyhedron. Convex in the sense of mean curvature, but mean curvature sounds like you still need derivative, but actually convex, this concept can be like at least, you know, to have like positive mean curvature. That's a C0 condition. That's something I want to emphasize. That's a C0 concept. I mean, C0, I mean, you don't need the derivative, okay? So this, well, that's what it means, okay? And of course, angle is also a C0 concept. You see, so this is like, it already provides like a much more flexible way of defining what non-negative scalar curvature is, okay? So another reason, you know, these things make sense was there were recent results. Like if you have a sequence of smooth metric which converges to another smooth metric, but only in C0, which means uniformly converge. There's no derivative involved. If the scalar curvature for GI is non-negative, then the scalar curvature of G is also non-negative. So that's very much in the same spirit. That's very striking. So it means that negative. Oh, did I say something wrong here? Non-negative, sorry. No, this is non-negative. Okay, sorry about this. Non-negative curvature is a C0 property. Okay, should be very flexible. Okay, so that's just like a more conceptual like motivation. But let me also give like another argument, proof of an important theorem of Zhang and Yao, like the positive mass problem, you know, based on Gromov's conjecture. So, so this Dihedral extremality or rigidity, this theorem, I mean, this can be considered as a localization of the positive mass problem. And so by a reduction result of Lohacam, so the positive mass problem can be reduced to the case you have one end and it's like Euclidean outside a compact set or Euclidean at the infinity. But also the scalar curvature inside is like is positive. Okay. Then what you can do is you can just have like a big box or polyhedron, like and put the non-Euclidean part inside. Okay. Now you just do a comparison. You apply the comparison. You know that, but this, of course, this kind of argument was also in an article of. This was essentially in an article of Nature. Okay, so again, I have to acknowledge I'm not an expert in differential geometry. I'm like a student learning the subject. So anything I said wrong about history or the subject, please let me know. I'm looking at everything from like my own point of view, which is can be very sometimes can be misleading. Okay, so let me just mention what's previously what's known about this dihedral conjecture. Gromov initially cubes and Li Chao, and well, I'm just giving some very like a typical example, Li Chao and some other simplices and other like other polyhedrons. I'm okay. And the method is based on Zhang and Yao's minimum surface method. Okay. Okay. So I'm going to okay. So I'm going to next. I'm going to like try to prove like a general theorem, which what implies the dihedral extremality conjecture in general. Okay, so the method is quite different. Okay, so it's we use the Dirac operator and operate series stuff like that. But before I go on, are there any questions?
So I remember that Witten had an approach to the positive mass theorem using Dirac operators, and I wonder if there's a relation to what you're doing.
Oh, yes, Asa, that's a very good question. Actually, they are spiritual connection. I will explain the spiritual connection. Yeah. So, yeah. So there are there are some spiritual connection. I will explain. Asa made an excellent point. Okay, so let me just, in case, probably everyone knows what the Dirac operator is, but just in case. So So what is a Dirac operator in Rn? So it's actually, it's in a way, it's just a square root, the square root of the Laplacian operator. Okay, so you just find, you know, a first order differential operator with coefficients, matrices, like, and satisfying this kind of equation. And now one thing I want to like point out in proving, you know, that D square is the Laplacian. What we are using is like, I think this is called the Guoliang theorem. It's a name to that. You know, take partial derivative in different orders, they still give you the same result. Okay. Now this, of course, we take this for granted in the Euclidean space, but that's not true in general for manifold. And the, you know, the difference is exactly curvature. Okay. So when we define the Dirac operator on a general manifold by just imitating, you know, what we did by replacing partial derivative by covariant derivative, when you square it, you expect curvature to appear just because, you know, in a general manifold, partial derivative don't commute with each other. And that's what the curvature is, you know, from operator theory point of view. Okay, I'm not going to specify what curvature is. Actually, for the so-called spinor bundle, it's exactly scalar curvature. But if you have a general bundle, it's some kind of curvature. It's, yeah, some more general curvature involved with the bundle. Okay. All right, so that's the Dirac operator. You know, one thing is, you know, if this curvature data is non-negative, then or positive, then, you know, D is invertible. Well, and we have all sorts of way of like detecting when it's not invertible. So that's how you kind of operate theory on comes in. Okay, so that's everything about Dirac operator. Is there any question about Dirac operator? I understand most of you are already experts in the subject. So, but if in case there's a student, if there are questions, please let me know. Okay. All right, I'm going to outline the proof. Okay, proof of the Dihedral conjecture. So this is joint work. Oops, sorry. Okay, so this is joint work with, Jinmin Wang, and who was my former PhD student, but currently he is a postdoc, Zhizhang. So Zhizhang is my young colleague in Texas. Okay. Okay, so I'm going to outline a proof. Now, when we got started on this project, somehow we were very confident that we should be able to do it because, you know, the main problem is like the corner, the singularity with corners. But with my background, mathematical background, we are confident our ability about like dealing with singularity, you know, especially non-commutative geometry, we do all sorts of singularity. So that gives us a lot of confidence. But still, we struggled, like how do you make Dihedral angle? How do you like derive the angle from the operator? And that's something we struggled for a long time. Okay, we came up, we experimented with all sorts of methods. We constructed some non-commutative algebra, which kind of encodes the information about Dihedral angle. And we also, because we had some background in like classical harmonic analysis, we also tried that. But in the end, Dihedral angle actually appears very naturally. And so this is the key estimate. This is, so this equation. Let me just explain. So we apply the Dirac operator, of course, on a closed manifold. On a closed manifold, what do you have? If it's a closed manifold, what you have is just essentially the first two terms, nothing else. Okay. If it's a closed manifold, that's a classical. It's an equality even. Okay. But since we have like a manifold with corners, so this is true in general with manifold with corners, has nothing to do with like being a polyhedron. Okay. And of course there is, you know, like from Stokes' theorem, you have some boundary contribution. Okay. And this is this term here, this is the Dirac operator on the boundary. And then you have also something coming from the mean curvature. And so here, so the last term, that's something we struggled for a long time, is something with dihedral angle. Okay. Now, just looking back, and it's not surprising. Actually, the dihedral angle is, it can be interpreted as some kind of distributional mean curvature at the corners. Okay, that's something I think probably in classical differential geometry we don't do this, but you know, so this it's really a distributional like mean curvature. Okay, so if you interpret this as a distribution of mean curvature, then it's part of the mean curvature data. Okay, then yeah, it's not surprising. Okay, all right. So I'm not going to like, this is like the proof. I think maybe I mentioned one key idea. So what do you do with a corner like this? And so what we do is we approximate the corner by something smooth. Okay. And then we do an approximation, and that's, you know, that's what we do in analysis, right? So in like distributional sense, well, it's some kind of, yeah, very much along this spirit. So okay, so this is the closure estimate. Okay, so now with this estimate, so we can, now let me outline the proof.
Could you explain what G and G0 are?
Sorry.
What are G and G0?
Oh, sorry. So G and G0 here is, let me draw just a picture. So if, okay, so let me draw a picture. Let's see, we have like a cube like this. So let's see. So first of all, G is the Riemannian metric. And G0 is the Euclidean metric. So that's what we are comparing. Okay, so Fi, oops, Fi is just the codimension phase, codimension one phase. Okay, so, and so if like the bottom phase, let's say the bottom phase is Fi, the side phase is Fj, then this is theta, the angle theta ij. I mean, it's pointwise. It's a pointwise thing. So it's with respect to different metrics. With so yeah, that's the angle. So if for, of course, for if I have G0, the Euclidean space, if I put us like a cube like this would be 90 degrees. And I should also mention Gromov proved more than the cube. In he like in many of the articles he touched on this subject. At some point he proved the conjecture, like when the angles are like rational multiple of pi or something, because his argument is very geometric, so somehow he has to use the rationality. Okay, so these are the notations. Any other question about the notations? There are quite some notations here. H is the mean curvature here. Okay. All right. So now, so I actually one thing so S is a spinor bundle. So we are considering the Dirac operator on the spinor bundle tensor with a spinor bundle. So in this case, actually, you can identify the bundle with just the bundle of exterior differential. Okay. All right. So we need to impose like a local boundary condition. So local boundary condition is, in this case, it's a very classical boundary condition. We require the forms to be tangential on the boundary. Okay. Okay. Maybe say was Fredholm is like whenever you have an operator. Okay, sorry. So Fredholm is it's about really solving linear system of equations. If you have a linear operator, say, if you try to solve like the linear system, like T psi is eta, so then we have to worry about, do we have a solution? Our solution unique or not? And the uniqueness is about kernel, okay? And actually,
Guoliang,
is Fredholm. And it turns out it's just the Euler numbers of Fredholm. Okay, so this must be your favorite invariant. Okay, so two of our most favorite invariants, they are the same. Okay, now if like the polyhedron is convex, or more generally, if the Euler number is non-zero, okay, then from the definition of the Fredholm index, we know there is a non-trivial solution for this. Okay, now, so this is very much, of course, in the spirit of index theorem. Index theorem is in general, I mean, of course, you're trying to, it's about solving differential equations, but it's very hard to solve. But on the other hand, the Fredholm index normally is easier to compute, just because the Fredholm index is invariant under continuous deformation. Okay, so here it's also such a case. All right, now if you have a non-trivial section, a non-zero section, so from our estimate, so on the left-hand side, it's going to be 0, right? Now, but on the right-hand side, because of the condition in the dihedral conjecture, you are assuming scalar curvature is non-negative. You're also assuming, that from the comparison of dihedral angle, which means that the last term is also non-negative. So then it's a sum. So you have 0 here, you have also everything is non-negative, each of the term is non-negative. So that means all the terms have to be 0, right? So it means this is 0, that scalar curvature is 0, that's 0. Now the first thing is 0 means it's kind of parallel. So it means if it's a non-trivial section, it's point-wise like non-trivial, non-zero, okay? Now, if it's point-wise non-zero from the second equation, we know already scalar curvature by assumption is non-negative. Then the scalar curvature has to be identically 0. The same is true for mean curvature, and the same is true for the angle, okay? So that's how you conclude. So it's from like some kind of positive or Volcano type of argument. Okay, so that's that's the spirit I was mentioning. It's the proof like use the same positivity idea like in Witten's proof of the positive mass theorem, and it shares that same spirit. It's like the positivity. Okay.
Very interesting.
Okay, so is there any question about the proof? I would say this proof is quite elementary. Any question? Okay. Now, so I just explained like a very kind of special case of a general theorem. So let me just now mention the general theorem. Okay, the general theorem looks more technical. I did not like, we can in some cases draw like stronger conclusion, but I will not try to do this. So it's about comparison of two manifolds with corners. So that's with corners. Okay. So you compare like the scalar curvature. Oops. Yeah. Scalar curvature like, well, I mean, the special case we were considering is the second manifold is just polyhedron with Euclidean metric. So then, in this theorem, all the right-hand side is 0. Okay, but here we have a little bit more general. But you see, it's just the most natural generalization. We assume that it has the second manifold that has non-zero Euler number, then the so-called A degree is non-zero. Well, if you don't know what it is, don't worry about it. Just then you have this kind of rigidity. Then they have to be exactly the same. Okay. Now, so the proof technically it's a little bit more complicated, but it's if we like understand the polyhedron case, then let that guide us. Then it follows the same spirit. I mean, somewhere in the analysis, for example, we have to like deal with the singularity at the corners, but that's not terrible. But the reason I wanted to explain the special case is that once we have a good understanding of the special case, then everything else is not, it's technicality, but it's not too bad. Yeah. Okay, so this is kind of the general theorem. Okay, so Asa, should I think I already spoken for 15 minutes. Should I stop here?
Oh, it's up to you.
So I prepared for a second part, which is in the same spirit. Maybe I just show you what I was going to. Okay, so again, it's about manifold with corner, but in this case, it's a special manifold with corner. It's like really a cube. Okay, so this so-called cube inequality on scalar curvature is like if you assume the scalar curvature is it's greater than or equal to some positive number k, then it implies something about distance, like the distance of opposite side of the cube. So this is a precise inequality. Okay, so let me just mention that Gromov proves this in dimension less than or equal to 8 using minimum surface method of Shang and Yao. So we actually give a general proof, but we actually proved a strict inequality. But this is actually optimal. Actually, there are examples you cannot do better than this. And again, you know, using Dirac operators, but the main difficulty is dealing with the singularity at the corners. Well, I just want to mention one thing is normally scalar curvature is not strong enough to imply anything about distance. So for me, that's quite very interesting. And another motivation of this is actually this is useful, like in some of their work, the non-existence of positive scalar curvature in aspherical manifold case. We hope we have been like discussing, hope this can be used in the high dimensional case. But since I'm running out of time, I will not talk about the proof. But it's a different way of like, so our way of dealing with singularity is different from what I explained earlier. Instead of like using boundary condition, we extend the metric, remaining metric to Euclidean space. Then we use like Dirac operator with a nice like potential. And so this is an analytical way of dealing with singularity instead of like imposing a boundary condition. So it's a different way. So yeah, well, maybe because my initial title of my talk is high invariant. I never mentioned the high invariant, but in this theorem, high invariant is there. So using like K-series of sister algebras, I will just put it there just to illustrate high invariant is like relevant. Well, thank you very much.
Well, thank you very much for a really interesting talk and a very inspiring one. I'm sure there'll be a great deal of discussion. So maybe I unshare your screen and we can all see each other. And
okay.
If you want to make a comment, please turn your video on so we can see you. And maybe I start by asking, these are interesting methods where you understand some of the analysis in a geometric way. Is there a possibility to use these ideas in the non-commutative setting?
Yes. So we actually tried very hard to do this. For example, on the second part, and also for non-existence of a spherical manifold. So the current work by geometers, they use minimum surface. We were trying to replace, we were trying to do it using like non-commutative method, which potentially could work in like high dimension, but it seems to be very much related to like some of the quantitative method in like studying the Novice conjecture or stuff like this. But so far we are still kind of struggling.
It's very interesting. Are there other comments? Elena, you seem to.
Yeah. So I would just ask actually the place you've stopped, because you mentioned some kind of higher K theory and this kind of invariance. It's very, very interesting. So maybe you just comment on this, how, because you didn't say details and maybe it's hard, but just to have an idea, right? What you do, what kind of sister algebras, what is the sister algebra which you associate to your construction?
Oh, the sister algebra is, it's just the usual one. It's just related to the fundamental group of some.
So this is the group sister algebra.
Yeah, it's the group sister algebra of some like submanifold.
Yeah, but then how they are related, right? Because you get some kind of higher structure. So I'm interested, like, what is this higher structure? How does it look like?
Oh, it's you kind of, at some point you need to deal with like, you need to know like if the Dirac operator is a high index in that context is 0 or not. So the invariant is just used as like an obstruction to invertibility of the operator.
Okay, but still you have to have some kind of sister algebra to look at K theory, right? So you have to have you have to capture the sister algebra somehow.
Yeah, so the sister algebra is there like to, it's used as like an invariant, because because in that case, like the usual Fredholm index might be 0.
Okay.
So we need some like more refined, high invariant.
Okay, thank you very much. Thank you.
So there are other comments or questions? Let's see.
Yeah, so again, I'm not an expert in differential geometry, so if I said anything wrong, let me know.
I see some very interesting people in the audience, but nobody wants to talk. That's often the case. But some people in Asia are very late at night. In any case, thank you so much, Guoliang. Oh, did somebody want to make a comment?
Maybe I just say people will start like an online seminar on on this kind of subject. So if anyone is interested, I don't know the schedule, so especially young people. So yeah, you're welcome to join. We probably people from different subjects, so we can learn from each other.
How do we find out about it?
So they have some organizational meeting this week. So I don't know the schedule yet. So so after the organizational meeting, so then I guess I think they will like post it online. I think it's probably a weekly seminar.
Good.
It's it's not local, so it's there are some of the organizers are from Europe, or so So especially for the students, if you're interested, yeah, welcome to join. It probably will start next semester, yeah.
Yeah. So thank you very much, Guoliang. It was fine talk for the end of our seminar series this term. And we look forward very much to continuing in January. January 25th will be our next talk, and see you then. Bye-bye. Bye-bye.
Bye-bye. Thank you.
So Guoliang, I'm afraid that I don't know what the gap was in the electricity here, but I lost electricity for a very short moment, but it turned my router off and it turned everything connected to me off, and the computer stopped recording and I lost the connection completely. Eventually I was back, but there's presumably a 5-minute gap and a couple of different recordings. I hope we can put something interesting together to put it onto the YouTube. You're muted, Guoliang.
I was just saying that this happens a lot with where I live now. So, but the house has a generator. So as soon as the electricity gets off, my generator automatically turn on. But the generator is kind of loud. I think it happens a lot here with.
My electricity was only off for a fraction of a second, but it affected my router and it affected the internet connection, and it took a while before things normalized again.
Mm.
So we'll have to work on this and try to get something good to put onto YouTube for you.
Yeah. Well, thank you, Asa. So I probably there will be, yeah, so similar talks by other people, yeah. I mean, at the seminar.
Zhizhang is still here. Maybe he's our expert at editing.
Okay.
But it's very early still in California.
Yeah. So this time is early in California. Yes. So the seminar I was talking about is like jointly, so it was Gromov's idea. So yeah. So probably there will be quite some talks on this subject.
Right. So let me see. I have to. Okay. So I guess I should disconnect and we'll talk. We need to talk a little about the plan for January, or if there's a plan for January. But
okay, if not, we think about March. Yeah.
Good. Bye-bye.
Okay, bye-bye. Bye-bye.